So we're going to look at the surface reactions, which are a very important part of the heterogeneous catalysis that we are going to learn in the upcoming lectures. We are going to relate the molecular events to the surfaces, how they interact, how the molecules interact with the catalyst surface, how do surface reactions proceed. Again, we are going to have a unimolecular A transforming to B, but this time we have a surface, a catalyst that expedites the rate of the reaction. Now I'm going to, for the sake of discussions of this lecture, I'm going to have a wiggly surface that will symbolically represent the catalyst. My catalyst is fully exposed. My molecule A from the gas phase comes and interacts with the surface and adsorbs on the surface. This interaction and adsorption is spontaneous and not activated at the elementary level. Because the catalyst surfaces, catalysts and their surfaces are in metastable states, that they possess a huge amount of energy that is embedded in the unsaturated surface bonds. Those surface bonds are very reactive, and the moment they see this species A, they are ready to interact. So we have A. This star symbol will represent an active site on the catalyst surface, and this is going to form a surface-bound species. This reaction, by its nature, is not activated if elementary, if it is a single step. And hence it's very fast, and hence it's mostly equilibrated. Then we have this adsorbed molecule going to do products. So I have step 1, step 2. One point I would like to stress is not to confuse this with the transition state theory. So this first step is equilibrated. Forward activation is 0. We have the reverse step that is activated, and this step has a measurable enthalpy change, and it is related to the heat of adsorption. This step is also activated. As well as the reverse step. So let's take the first equilibrated step. The first equilibrated step is going to be represented by a rate expression dictated by the elementary nature of the step. And I will write n star to indicate the number of sites that are available. This is going to be equal to the reverse rate at k reverse 1 times, I'm going to write n of A star. I use different symbolism because this concentration is the concentration in the gas phase or in the liquid phase domain. However, those n's refer to the ones that are on the solid surface of a catalyst. Na plus N star is equal to the total number of sites that were available in the beginning of the process. So I'm going to do a little bit of algebra, and then I will derive what we refer to as the Langmuir adsorption isotherm. I will divide both sides of this by N total, so that I have 1 on this side. I will use theta to reflect the fraction of the surface covered by A, and theta A and theta vacant will reflect the fraction of the surface that is vacant. And we assume here that the sites that are covered by A and the vacant sites are randomly distributed. And we also assume that all sites are equivalent. Okay, so here I have K forward 1, Ca N star, K reverse Na star. Doing this to here will also help me. I will have K forward 1, Ca. Now I call this theta vacant, and this is K reverse, and this is theta A. I will do a little bit more algebra here. Let me divide this board so that you're not confused. So I have K forward 1 times Ca times 1 minus theta A. I substituted for theta vacant from what we call the site balance. To be equal to K reverse 1 times theta A. As usual, I will divide this, and I will call this the equilibrium constant of the adsorption of A on the surface. So I have K equilibrium times Ca times 1 minus theta A to be equal to theta A. Or we have theta A to be equal to K equilibrium Ca divided by K equilibrium Ca plus 1. Theta A is fractional surface coverage. And the expression that we derived is called the Langmuir adsorption isotherm. Now, what am I going to do with this theta A? My second step is irreversible, and it is what we call the rate determining step. So the overall rate of this reaction is equal to the rate of the second reaction. K2 times Na star. What is NA star? It is theta A times N total. K2 N total times theta A. And we derived theta A in terms of the concentration of species A. So we have K2 N total times K equilibrium times Ca divided by 1 plus K equilibrium times Ca. Now this is our rate. We need to discuss the implications of such a rate, implications in terms of how it is influenced by temperature, how it is influenced by the concentration of the individual components. Now let us discuss the implications of the rate that we have derived in terms of the effect of temperatures and pressures. But first, let us understand what the isotherm expression mean to us. The adsorption isotherm, when we plot Ca as a function of theta A, has two critical behavioral domains. One domain is when concentrations are very low. When concentrations are very low, this term is very close to zero. So theta A is a linear function of concentration. So we have a linear increase. This domain sometimes is referred to as the Henry's law domain also. Do you remember Henry's law? Okay. The other domain is when this group is far bigger than 1. Then we ignore 1. They cancel one another, and theta A at very high concentrations is equal to 1. This is 1. So we have a mixed region in between. Okay, so this is the isotherm equation. Isotherm, it is called the isotherm because we keep the temperature constant. We keep the temperature constant. As a result, we maintain equilibrium constant. The functionality of equilibrium constant, and a temperature, if you remember, was something like this. All right? So, now this is the isotherm. This is how it behaves as a function of concentration of species A. Now let's see how our rate is going to behave as a function of temperature and as a function of concentration of species A. So this is our reaction. And on the other side, for this reaction, we derived the overall rate as K2 NT times K equilibrium times Ca divided by 1 plus K equilibrium times Ca. Now let's operate in a low concentration domain. Ca is low. So we have only the terms in the denominator. I will call this R overall 1 for low concentrations. This is going to be K2, this is K20, e to the minus E2 over RT times N total times K equilibrium, that is equal to K equilibrium 0 times e to the minus delta H 1 over RT, this one, times Ca. Now let's combine the terms that are independent of temperature together. That is going to be N total times K20, then times K equilibrium 0, K equilibrium 1, 0. Equilibrium constant of the first reaction, 0, times e to the minus E2, activation energy of the second step, plus delta H1, heat of adsorption of molecule A on the surface divided by RT times Ca. This is a constant. Total number of sites available by the catalyst. This is a constant. This is a constant. This is concentration dependency. And this is the observed activation energy. All right? So let's write here. The observed activation energy is E2 plus delta H1. The reaction is first order with respect to Ca. For low concentrations, my rate is K0 e to the minus E2 plus delta H times Ca. Then, of course, we have to get for higher concentrations of Ca and compare our estimations. So we needed to create some space on the board to see the facts side by side. This is our isotherm equation. Theta is equal to K equilibrium Ca divided by 1 plus K equilibrium Ca. Now I'm going to derive this expression for high concentrations of A. Now when Ca is high, we have this term much bigger than 1, and those two cancel, and our theta A is equal to close to 1. So our rate is now, let me just put them side by side. K2 times N total times 1. Our K2 is K20 times N total times e to the power minus E2 over RT. And our reaction is a zeroth order with respect to concentration of A. And our activation energy is plain E2. So our observed activation energy E2 here. And of course, you have understood by now that in this domain that is intermediate, we have activation energy is a function of concentration of A. And it's a very strong function of concentration of A. So now, we have to be very careful when dealing with catalytic reactions on how we measure our activation energies under which concentrations we measure the activation energies, and how we use those activation energies, how we generalize those activation energies, and also the reaction orders. You have seen that the reaction order has changed from first order to zeroth order, going from low concentration to a high concentration. And this analysis was valid for a constant temperature situation. Now let's see what is the reflection of temperature. Of course, we have over RT here. Now let's see what is the effect of temperature on the observed, measured activation energies. Here temperature enters into our picture through our equilibrium constant. This is K0 e to the minus delta H over RT. So this adsorption process, we said that, is non-activated if elementary, and as a result, the forward activation energy is 0, the reverse activation energy is obviously positive, so we have a positive reverse activation energy, 0 forward activation energy. The difference between forward and reverse is negative. As a result, adsorption is exothermic. If adsorption is exothermic, as the temperature increases, this term should decrease. So at higher temperatures, we are going to have smaller and smaller equilibrium constants. At high temperatures, when we make our rate measurements at high temperatures, we are going to be closer and closer to the Harry's law region. When we make the measurements at lower temperatures, we are going to have larger equilibrium constants. We will be closer to this side. So it depends on the delta H heat of adsorption of the molecule that we are dealing with. And if we have very large heats of adsorption of molecule A, it is going to induce dramatic changes between small temperature changes when we are measuring the activation energy. Remember how we were measuring the activation energy? We were measuring the rate of the reaction by changing the temperature of the domain of the system, and from that we were deducing the activation energy through an Arrhenius relationship. But you see, in the catalytic reactions, when we change the temperature, there is a risk of change in mechanism because of the adsorption process and how it is reflected in the surface coverage of the adsorbed intermediate.